In the previous video, we obtained this equivalent circuit of the induction machine. This fictitious resistor is actually our portal that connects the electric domain with the mechanical domain. So if the induction machine is working as a motor, the electrical power dissipated on this fictitious resistor is the mechanical power delivered by the motor to the load. If the induction machine is working as a generator, then the electrical power dissipated on this fictitious resistor is actually negative. It's dissipating a negative amount of power, right? Which means that the mechanical power is actually delivered from the load into the electrical circuit, right? And we obtained an explicit expression for the electrical representation of the mechanical power, which is Pm here, right? And it equals to the current squared, which is I2 prime squared, right? Multiplying the resistance, which is R2 prime, and then this term that depends upon the slip, right? And then you have to multiply 3. Don't forget to multiply 3. The reason you have to multiply 3 is because you have 3 phases. This diagram, this equivalent circuit, is just for one phase, and for 3-phase induction machine, you have 3 phases, right? So you have 3 duplicates of the same circuit. You have 3 these fictitious resistors, and on each of them you have a power that's like that. So you have to multiply 3 to obtain the entire power, the total power of the 3-phase induction machine, right? Once we obtain the mechanical power, right, the mechanical torque T on the rotor equals to the mechanical power divided by the angular speed of the rotor. And because the angular speed of the rotor can be expressed in terms of the synchronous speed, capital omega S here, and also the slip S. So after some algebraic simplifications, we can obtain this particular expression for the torque, for the mechanical torque, in terms of the slip, synchronous speed, R2 prime, and I2 prime, the current, right? So everything in this expression can be either measured using equipments or calculated. The current I2 prime needs to be calculated. This one has to be computed. The calculation of I2 prime using the exact equivalent circuit is a little bit complicated. So how are we going to compute this thing, right? We need to obtain basically the equivalent circuit of this branch, and these 3 branches, right? So we have like a 1 branch, 2nd branch, and then a 3rd branch, right? And then we need to obtain a equivalent component for these 3 branches connected in parallel, right? And if you look at this particular branch, it's 3 components connected in serial, right? So you have to sort of first obtain the equivalent component for this branch first, and then connect that to these 2 branches in parallel, and then get the equivalent component for these 3 branches connected in parallel. And then that component has to be connected with X1 and R1 in serial, right? You get the impedance for that. And then E1 divide the total impedance gives you the current gives you the main current that goes out here, right? And then that main current is split again at this particular junction, current junction, right? So what you have to do is to actually get voltage across here. How do you actually get the voltage across here? Once you got the main current, you can compute the voltage drop across this thing. The voltage drop across this thing, right? After these 2 voltage drops, you get the voltage here, right? And that's the voltage across this particular branch, right? Once you got that voltage, you can divide the impedance of these 3 components connected in serial, right? And then you get I2 prime. So the calculation is quite complicated. It will take some time to actually do this calculation, it can be done. It's it's feasible to actually get I2 prime using the exact circuit. It's not really it's just time consuming, but not really too difficult. Right? But to simplify the calculation, one approximation that people often take is to actually move this part of the circuit in front of R1 and X1. So basically just move the whole thing to the front. So this whole thing is moved in front of the X1 and R1. Here I have actually switched the locations of X1, R1 and X2 prime, R2 prime. Basically I'm putting the two inductors together and then put the two resistors together. But it's okay because everything is connected in serial, so I can actually just switch their places without affecting the I2 prime, basically. So once we have made this kind of simplification to the circuit, it becomes really simple because the voltage across these two terminals is E1, right? And then so the voltage across these two terminals, these two nodes, is also E1, right? So the voltage across this entire branch is E1, basically, right? After you have made these kind of simplifications. So you know the voltage across this entire branch with all those components connected in serial, with all 5 components connected in serial. That's E1. You know the voltage now, right? And then if you get the impedance for these 5 components connected in serial, you can get the I2 prime, right? Once you get the I2 prime, you can compute the torque, you can compute the power. So by doing this kind of simplification, you make the calculation a lot easier, right? And what's the error introduced by this simplification, right? You have actually changed the exact equivalent circuit to this approximate equivalent circuit, right? Usually, for machines with large horsepowers, this simplification introduces an error that's less than 10%. It's a very, very small error, right? It's a very, very small error. For small machines, for small induction machines, less than 5 horsepowers, you cannot do this simplification. The error could be quite large. But for wind turbine, for the induction machines used in wind turbines, this simplification introduces negligible errors, right? So by just moving this part of the circuit to the front of the circuit, to the front of the entire circuit, you can make the calculation a lot easier, and the error introduced is less than 10%, right? So once we obtain the solution for the I2 prime, we can bring it into the expression for the power and the torque, right? And the exact expression for the torque is still quite long, right? It's still quite long. In practice, this expression is not presented as an equation, but presented as a curve, the so-called torque slip curve. So the vertical axis is usually torque, and then horizontal axis is depends upon how you actually present the curve. It could be just a slip, right? Or it could be rotational speed of the rotor. Depends. It depends how you actually present the curve. So the exact expression for the torque is going to involve E1, the input voltage, R1, that's the stator side resistance, R2 prime, that's the apparent resistance of the rotor to the stator side, X1, that's the flux leakage on the stator side, X2 prime, that's the apparent flux leakage on the rotor side reflected on the stator side, right? And then slip, S is the slip, right? So the exact expression for the torque is going to involve all those terms, right? But you can think of the slip as the only independent variable, and then the only dependent variable is the torque. And everything else, including the voltage, the resistances, the inductances, the reactances, can all be considered as just the parameters to that curve. So depending upon the exact values of those parameters, the shape of the curve are going to change. But the curve that we're going to examine is just the torque with respect to the slip, right? And then once you are given a set of values for those parameters, the shape of the curve, TS curve, is fixed. So the torque slip curve is gonna look very much like that. It's just gonna, if we make a plot of the torque for every different values of slip, the curve is gonna look like that, right? And suppose you are given a set of values for those parameters. So those parameters have fixed values, right? And then if you plot the torque as a function of slip, the curve is gonna look more or less like that, like this kind of thing, right? So here horizontal axis is the slip, the vertical axis is the torque, right? It can also be presented in a slightly different way. So here the horizontal axis is rotor speed. It's not slip anymore, it's rotor speed actually. So going this way, the rotor speed actually increases from 0 to like 2ns on this particular graph. It can go even above 2ns, but it doesn't matter. Here the rotor speed goes from like a 0 to like minus ns. Ns is what? Ns is the synchronous speed. It's the rotational speed of the magnetic field created inside the stator. Right. So as the rotor speed increases from 0, the speed difference between the rotating magnetic field and the rotating rotor decreases, which means the slip also decreases. So as you actually go this way, the rotor speed increases, but the slip actually decreases. So you can sort of see here, right? At rotor speed 0, which is the standstill condition, right? Rotor is not rotating at all; it's stationary. The slip is 1. The slip is unity, right? But as you actually increase the speed of the rotor, the rotational speed of the rotor, slip actually decreases, right? So S from 1 to 0. To 0 means what? Slip 0 means there's no difference between the rotating magnetic field and the rotating rotor, right? So the rotor at this particular slip, the rotor actually has a speed of synchronous speed, right? And then if you increase the speed even further, if you increase the rotor speed even further, synchronous speed doesn't change, right? The speed of the rotating magnetic field doesn't change. So as you increase the rotor speed even further, the slip becomes negative now, right? So this part of the axis is actually equivalent to this part of the axis on this figure, right? So as the rotor speed increases, slip decreases from 1 to 0 to a negative number, right? So that's why the horizontal axis on this kind of presentation is exactly the opposite of the horizontal axis on this kind of presentation, right? This presentation, horizontal axis is slip. So slip increases in this direction, right? But in this kind of presentation, the horizontal axis is the rotor speed. So slip actually decreases in this direction, right? So that's why the curves look exactly like a mirror image to each other, right? Because the horizontal axis is actually exactly the opposite of each other, right? So the 2 points that are worth mentioning, one is the slip equals to 0, no, rotor speed equals to 0, standstill condition. Slip equals to 1, right? This point actually corresponds to this point on this particular presentation, right? And at this particular point, the torque, so the torque at standstill condition, when slip equals to 1, is called the starting torque. Right? It has a special name. It's called starting torque, which is the torque at the standstill condition when rotor speed is 0 and the slip equals to 1. Right? And that's called starting torque. And another point of interest is just this point when slip equals to 0. So rotor is rotating at exactly the same speed as the synchronous speed. So in this case, the rotor is rotating with the same speed as the magnetic field in the stator. So the rotor is not really cutting the magnetic field. So there's no induced voltage, there's no induced current inside the rotor. right? So there's no induced Lorentz force inside the rotor. So there's no torque. If there's no induced Lorentz force, then there is no torque. Right? Torque is force times the radius, right? So radius is non-zero, right? But the force is 0, so the torque is 0, right? So at this particular point, the torque is exactly 0, no torque at all, right? And then depending upon the slip value and the rotor speed, you have 3 different zones, right? So when slip actually is less than 0, which means the rotor is rotating faster than the synchronous speed, right? The slip is defined as what? The slip is defined as the synchronous speed subtract the rotor speed and then divide by the synchronous speed, right? So when rotor is rotating faster than the synchronous speed, then S is going to be less than 0. And in this kind of situation, the torque is negative. The torque is negative means what, right? The torque is negative. Back in video 17, we talked about negative torque, right? Negative torque means the torque is in the opposite direction, of the rotational speed of the shaft, right? So shaft is, for example, rotating clockwise, but the torque in this region is actually counterclockwise, right? But why is that? Right? If the shaft is rotating clockwise, then there must be another torque that's rotating clockwise, right? To sustain this kind of clockwise rotation. What exactly is that torque, right? What exactly is that torque? That torque is the torque provided by the wind turbine rotor. So the wind turbine rotor is rotating, and it's actually supplying the clockwise torque, right? So in this kind of situation, in the generating region, the torque that we are looking at, the negative torque that we're looking at here, is actually acting as the back torque that's countering the torque that's provided by the wind turbine rotor, right? So in this region, the torque we are looking at is the counter torque of the torque of the rotor, right? So it's very, very important for us to understand why the torque is negative in the generating region, right? So slip is less than 0, right? This region corresponds to this particular region, right? On this particular graph, right? They are basically the same thing, right? So slip is negative here, slip is negative here, right? And if you have any doubts about those different zones, the braking zone, the motoring zone, and the generating zone, you can go back to take a look at the video 17, in which we talk about the torque and the back torque, right? And and of course, when torque is negative, the power is also negative, right? Power is negative. So when S is negative, one subtract S is positive, right? But S is negative, so the power is negative, right? So when torque is negative, the power is also negative. So when a negative power means what? It means the resistor is dissipating negative energy, right? Dissipating negative energy means that it's actually creating energy, right? And that energy is actually delivered by the rotating shaft that's driven by the wind turbine rotor, right? So another thing that we have to sort of pay attention to is that for the negative slip region, the shape of the curve is exactly the mirror image of the shape of the torque slip curve in the positive slip region, right? So it's antisymmetric, right? So in the following, we're going to just focus on this quadrant. We're just going to look at the positive slip. But we have to sort of keep in mind that the results we obtained for the positive slip region is also applicable to the negative slip region because they are symmetric. It's antisymmetric, right? So if we derive anything on the positive slip side, it's also applicable to the negative slip side, right? The next thing we're going to talk about for the torque slip curves is about the separation of stable regions and unstable regions, right? So we're just going to look at the positive quadrant, positive slip side, but you can imagine on the negative slip side, the curve is exactly the mirror image. It's symmetric, right? So the stable region for the positive slip can be actually mirror imaged to the negative slip side, right? So what's actually the stable region, right? The stable region is from slip equal to 0 to the slip equals to SM. SM is what? SM is actually the slip at the maximum torque. So Tm is the maximum torque. And corresponding to Tm, you have a slip that's SM. So the stable region is from slip equal to 0 to slip equal to SM. Right? And then the unstable region is the slip that's larger than SM. Right? So why do we have this kind of distinction, right? Why do we have this kind of distinction? What does it mean by a stable region and what's actually an unstable region, right? Suppose we would like to keep the torque at the level of TFL, full load, right? TFL is the full load torque, right? Suppose we would like to maintain the torque at this particular level, right? And then there are two slip values correspond to this particular torque value, right? One is at the location C, and location C is gonna have a slip value that corresponds to location C, right? If you look at the horizontal axis of point C, it's gonna have a slip value, right? And then the other point is at point D. Point D is also gonna correspond to a slip value. You're gonna also have a slip value for position D, right? So there are two slip values that can allow us to reach this particular torque value. Point C is inside the stable zone. It's from 0 to SM, right? But point D is in the unstable zone. So these 2 points are, even though they give you the same torque value, but they are actually in different zones. Let's look at the point C in the stable zone. So right. So the slip is at SC, suppose, right? So if for some reason the slip increased by a little bit, which means suppose the slip actually increased to this particular location, right? And then the torque is going to increase. Slip increase means what? Slip increase means rotor speed has decreased, right? So slip and the torque, rotor speed actually goes in opposite direction. So if you increase the slip by just a little bit, it means that the rotor speed has decreased a little bit, right? And if you look at the torque actually goes up a little bit. The torque increased a little bit, right? If you increase the torque, then it's going to drag. You are going to have more torque on the rotor, right? So the rotor is going to speed up. Rotor speed up means slip is going to decrease, right? So you perturb the slip by increasing the slip a little bit. Now the increased torque is going to increase the rotor speed, is going to decrease the slip back, right? So if you have a small perturbation in the positive side, that perturbation, the increased torque is going to drag the state of the machine back to point C, right? The same is true if you have a little decrease in slip. Suppose for some reason the slip is decreased a little bit, right? If the slip is decreased a little bit, which means what? Which means the rotor speed is increased a little bit, right? If the rotor rotates faster, then the slip is going to be sort of smaller, right? And what's going to happen, right? What's going to happen? The torque is going to decrease, right? As soon as the torque decreases, the rotor speed is going to decrease, right? The rotor speed decreases, the slip is going to increase, right? So the state of the machine is going to go back to point C also, right? So for points, for states within this stable region, if you have a small perturbation in slip, it's always going to go back to the position that you started with. It's going to maintain the torque that you started with, right? So that's the meaning of a stable, right? A stable region. But the situation is very different for the point D, which is in the unstable zone, right? So if for some reason the slip increased a little bit, right? If for some reason the slip increased a little bit, which corresponds to a decrease in rotor speed, right? Then the torque also decreases. If we follow the curve, the torque also decreases, right? If the torque decreases, the rotor is going to slow down, right? It's going to slow down even further, and the motor will deviate from point D even further, right? And on the other hand, if the slip decreased a little bit, which corresponds to an increase in rotor speed, right, then the torque is going to increase, which will speed up the rotor even further, and the motor will deviate from point D even further, right? So in the unstable region, if you have a little bit deviation, the deviation is going to sort of increase. It's going to sort of deviate away from the point that you started with. So that's what unstable actually means, right? And the same analysis also applies to the generating mode, right? So for the generating mode, you also have a stable zone that's along this curve, right? Almost like a straight line, right? And then the unstable zone is like going off the screen now, right? So in practice, we must always keep the induction machine inside the stable region. We don't want to go into the unstable region. We want to stay in the stable region, whether for the motoring mode or for the generating mode, right? We want to stay on this straight line. We want to stay on this straight line. In the motoring mode, slip equals larger than 0, right? And also in the generating mode, on this side of on the smaller than 0 side of the curve, there's also almost straight line, right? Now let's look at how the torque slip curve is going to change with increasing input voltage E1, right? As the voltage increases, the amplitude of the curve is going to increase, right? So the location of the peak, the slip Sn, the location that's corresponding to the maximum torque, is not going to shift, right? So the peak stays at the same location, but the amplitude of the peak, the size of the torque, is going to increase with increasing voltage, right? The same is also true for the generating mode. So when slip is negative, this kind of observation also applies, right? So the amplitude of the back torque also increases with increasing voltage, right? And then the torque slip curve also changes with the apparent rotor resistance R2 prime. So if we increase R2 prime, then the location of the peak shifts to the right. So Sn, the slip corresponding to maximum torque, is going to shift to the right, right? But the value of the maximum torque is not going to change. So the maximum torque is still the same, right? But it's just the slip that's needed in order to reach the maximum torque is going to move to the right, right? So there are several consequences of this increase in rotor resistance. First, the starting torque increases. What exactly is the starting torque, right? That's the torque when the rotor speed is 0. When the rotor speed is 0, the slip equals to 1. Right? That's torque at this particular location. Right? So as resistance increases, R2 prime increases, so the curve is going to go this way, right? So the starting torque is going to increase, right? And the second consequence is that the slip range of the stable region increases, right? What we're saying is that the stable range is from slip 0 to Sn, to the slip that's corresponding to the maximum torque, right? That's the stable region. So as you increase the resistance, the range of the stable zone also increases, right? And then the third, because the dissipated power equals to the current squared multiplying the resistance. So if you increase the resistance, the copper losses, the dissipated power by the resistance is also going to increase, right? So the overall efficiency of the motor is going to decrease, and that's undesirable. So if the rotor can be connected to a one application of this particular analysis is that if the rotor has windings on it, it's a wounded rotor, then you can connect a variable external resistor to it, right? At the starting stage, we can use a high resistance, which is going to give you a large starting torque, right? If you are using the machine as a motor, you might want to have a very large starting torque, so it can start to rotate, right? So as soon as the rotor reaches the target torque, we can immediately reduce the external resistance, and then the power dissipation is minimized and the efficiency is maximized during the stable operation of that motor, right? So that's one example application of this particular analysis, right? So now let's look at a specific example that's adapted from this particular book, right? So the equivalent circuit of our, so we are now using the induction machine as a generator. So this is the equivalent circuit of the generator, of the induction generator, right? And if you take a look at the exact graph, we have actually combined the two inductors into like a 1. So x equals to x1 plus x2 prime wiggle, right? And it has a value of 6j. It's a complex number, right? That's the reactance of the inductor, right? And then the values for the different inductors and resistors in the equivalent circuit, right? This is the approximate equivalent circuit, right? How do I know? Because this branch is at the beginning of the circuit, right? That's an approximate equivalent circuit, right? So the rotor speed, the rotor has a rotational speed that's 1845 RPM, and the synchronous speed is 1800 RPM, right? So our goal is to actually compute the conversion efficiency of this particular induction generator, right? So the first thing we're going to compute is the slip. So the slip equals to the synchronous speed subtract the rotor speed divided by the synchronous speed, right? So that's 1800 subtract 1845 divided by 1800. Right? So it's going to give you a negative slip minus 0.025. Right? It's a negative slip, so it's working in the generator mode. Right? It's an induction generator. Then the second step is what? The second step is to obtain the net resistance of this entire branch. This branch. Right? Starting from here, goes along, passing this fictitious resistor, and then goes back here. We want to get the net resistance of this particular branch, which is quite easy. All we have to do is to actually add up the resistance as we see it, right? Here R1 equals to 1.5 plus R2 prime, that's 1.2, and then plus the resistance of this fictitious resistor. And because the slip is actually a negative number, right? So 1 subtract the negative number is a positive number, and then divide a negative number, that's a negative number. So this resistor actually has a negative, a minus 41 ohm. This is the resistance of this particular fictitious resistor. Right? In reality, you cannot manufacture a resistor with this kind of negative resistance, but in this particular circuit, this resistor is actually our portal to the mechanical world. So a negative resistance actually means that it's going to receive power from the mechanical domain. Right? So if we add them up, we obtain a minus 46.5 ohm. Right? That's the net resistance. The third step is to actually get the impedance of this particular branch. Don't forget we also have an inductor here. Right? The inductor has an impedance which is actually a complex number, 6J here. Right? So the impedance is Rn, the net resistance, which is purely real, plus Jx, right? So oh, I see. There should not be a J here, right? Or there should be a not a J here. So you have to get rid of this J, or get rid of this J, right? So X actually equals to 6 ohm. So 6 times J, right? Because the impedance or the impedance on the inductor is an imaginary number, right? So it should be 6J here. Right, X equals to 6, not 6J. Xe should be equal to 6. So it's minus 46.5 plus 6J. Right, that's the impedance of this particular branch, right? And then we need to get the length of this particular complex number. How do we actually get the length of the complex number, right? So the length of this complex number equals to the real part squared plus the imaginary part squared, and then take the square root. So 46.5 squared plus 6 squared, and then take the square root, which is about 46.88 ohm. Right? If you don't exactly remember how to, what's actually the meaning of the length of a complex number and how to do that, how to compute it, you can take a look at the video 19, in which I reviewed the operations on the complex numbers. Right. Once we got the effective impedance, on this branch, we can compute the current on this branch. Don't forget we have the voltage across this branch already, which is 254, right? And then all we have to do is to divide the effective impedance, the length of the impedance, that's 46.88, right? And then we get the effective current. That's about 5.42 amps. Right. So once we got the current, I2 prime, then everything becomes quite straightforward, right? So the power on this fictitious resistor can be obtained, right? It's just the current squared multiply the resistance. And don't forget the resistance is actually a negative number here, right? So power squared, current squared multiply R2 prime, that's 1.2, and then 1 subtract S divided by S, that's minus 41. Which gives you a power, that's a negative number, minus 1445 watts. And that's the mechanical input. That's the power that's coming from the mechanical world. It's the power supplied by the wind turbine rotor, the mechanical power that goes into this particular circuit. It's a negative power, which means this resistor is dissipating negative energy, which means it's generating energy into this particular circuit. But we are not done yet. There are losses. We have to account for those losses, right? So the first loss is the copper loss in the rotor. So the rotor has some resistance, right? That's R2 prime, right? So you have losses, right? So I2 prime squared times R2 prime, that's the copper loss inside the rotor, which is about 35.2 watts, right? So the rotor is going to receive this much power from the mechanical world, and then it's going to dissipate this much of power because of its own resistance. So the net power that goes from the rotor to the stator across the air gap is just a summation of these two numbers. Right? A negative number and a positive number gives you a minus 1410 watts about, right? So that's the amount of power that actually goes into the stator. So that's the power delivered from the rotor to the stator. 1410 watts. Right. And there are losses in the stator too, right? Before the power actually goes from the stator to the power lines, that eventually goes into some kind of electrical load. For example, that's gonna go into a power plant or something, right? You have to sort of account for the losses in the stator too. So there are copper losses in the stator, because the stator has a resistance of 1.5 ohm, right? So current squared times 1.5 ohm, that's 44.1 watts. So that's the copper loss inside the stator. And then because the stator has to induce a magnetic current, a magnetic flux inside of it, so there are core losses in the stator. right? Those core losses are due to the hysteresis and also eddy current losses inside the stator core. And this loss is accounted for by this R0, which has a resistance of 900 ohms. Right? And then the core losses in the stator equals to what? Equals to the voltage across this branch squared divided by the resistance. Right? This equation is actually equivalent to this kind of equation, right? But it's actually using voltage instead of the current. So if you don't remember how we actually got this kind of equation, you can go back to video 18. We have a derivation over there, right? We know the voltage across this branch is 254 volts squared and then divided by 900, which gives you 71.7 watts. That's the core losses in the stator, right? And then if you account for all those losses, both in the rotor and in the stator, then the power that's actually delivered to the power lines from this particular induction generator is, so the power that goes from the rotor to the stator across the air gap, plus the copper losses in the stator, plus the core losses in the stator. Right, it's a minus 1410 plus 44.1 plus 71.7, which gives you a minus 1294 watts. That's the actual electrical power that goes into the main line, goes into the power line. Right? And then in order to actually get the efficiency, you have to use this number. That's the actual power that goes to the power line. Divide the mechanical power that comes into the rotor. The mechanical power that comes into the rotor is the power that's dissipated on this fictitious resistor, and this number we obtained already, right? That's minus 1445 here. Right? If we divide these two numbers, we get a number that's 0.895. That's 89.5%. Right? It's very, very high efficiency. And the induction machines used in utility scale wind turbines often have an efficiency that is even higher than this number, which can reach like more than 90%. Sometimes not more than 95%, actually. Right?